So, hello everyone. So, today we will be starting the second part of product formation kinetics. So, if you remember in the last lecture, we discussed unstructured kinetic model for the product formation, and next we discuss chemically structured product formation kinetic model. And today we are going to discuss further the structured kinetic model. So, first one we will be discussing this genetically structured, where we will be focusing on transcription and translation part, and then we will see this filamentous microbe model, because it is difficult to model the growth as well as the product formation for the molds, particularly using the other kinetic models. So, first what is genetically structured model? As we know, this unstructured model, it ignore intercellular details, and what we discuss structured model, it incorporates enzymes or metabolic pools. It may be based on the function or it may be based on the structure. Now, this genetically structured model, it go ahead one step further. What it does? It represents the actual molecular event, let us say transcription and translation, and tie gene level parameter to overall product formation. So, this is very important, particularly when your metabolite is protein. So, we can very easily apply this genetically structured model, because this, as you know, that transcription leads to synthesis of mRNA and translation further leads to synthesis of proteins. And if your product itself is protein, so this model can be easily applied. So, this says once you are modeling that molecular events, so it model becomes more robust under varying conditions, and here we are able to directly map the genetic changes to the product formation kinetics. So, as we discussed, this model describes product formation based on molecular mechanism of gene expression, and what it is going to incorporate? It is going to incorporate transcription and translation kinetics to predict protein synthesis, and as I told earlier, it is useful for modeling recombinant protein production and also useful for metabolic engineering. So, when we do model at molecular level, so basically we are focusing on gene expression. So, there are few steps. First is the promoter activity, second is repressor and inducer interactions, and third one is mRNA and protein synthesis. So, this part you can recall your molecular biology concepts, and ultimately if you are able to model this, it helps us to understand how genetic regulation affects the product formation. Now, in the case of protein synthesis, what are the molecular events? So, we can divide into two sub processes: transcription, where DNA is converted to mRNA, and translation, whether mRNA produces protein. Now, what will be there in the intracellular pool? We are going to consider the molar concentration of mRNA and molar concentration of active protein. So, we are going to consider two intracellular pool, mRNA as well as protein, and these are the few parameters which we will be using in the rate equations. The synthesis rate Kp and Kq, deactivation rate Kd and Ke, and dilution by growth is mu. So, Kp we will be using for transcription, KQ you will be using for translation. Similarly, for the decay of mRNA we will be using KD, and for the decay of protein you will be using KE. Mu will be common in both the cases. So, first we will see a transcription balance. So, d mRNA, this is the concentration of mRNA, equals to Kp eta into G. G is a particular gene, it says gene copy number concentration. Kp is transcription rate, what we discuss is synthesis rate Kp. Kd, further what happens during the synthesis, there is a deactivation as well, or so Kd is the deactivation into mRNA, and further there is a dilution by growth mu mRNA. So, these two are the negative term and this is your synthesis term. In addition, it is very important, there is a term eta, it is a promoter utilizing efficiency. So, it says of course, it is proportional to the G, but at the same time this parameter is very important, what is the efficiency. And what we are assuming here is, as you can see, rate is directly proportional to the concentration. So, we are assuming it follows the first order kinetics. Now, next we go for this translation balance. So, dP upon dt, rate of product formation, Kq in the synthesis rate proportional to the concentration of mRNA, and this is the utilization of mRNA at ribosomes. So, protein synthesis is taking place at the ribosomes. So, earlier we had the efficiency factor eta, that is the promoter utilization efficiency, and here we have the psi, that is the efficiency of utilization of mRNA at ribosomes, plus this is the deactivation, and last term is the dilution. So, these are very simple kinetics for both the transcription and translation. Now, look at the steady state. At the steady state, what are the factors which are going to affect the protein biosynthesis? Is the concentration of mRNA and efficiency of utilization of mRNA at ribosomes. Now, let us assume the balanced growth. What does it mean? It means the rate of accumulation will be 0. So, dm RNA upon dt equals 0 and dp upon dt equals 0. So, this leads to the calculate the value of product formation. This is a function of Kp, Kq synthesis rate of mRNA, synthesis rate of protein into G, what is the concentration of the active gene which is participating in addition these two efficiencies also there, and then this is directly proportional and it is inversely proportional to the deactivation rate of mRNA and deactivation rate of protein. So, this equation explains how intercellular product concentration directly in terms of parameters which influence the gene expression and mRNA and product stability in the cell. It is very important that we are directly able to link with the promoter efficiency to the protein level. So, you just see protein is directly proportional to the eta. Now, let us see in the case of E. coli, the gene expression rate is limited at the level of transcription. So, this is the rate determining step, and consequently the rate of expression of an operon regulated gene demands on the efficiency of transcription of the gene, which in turn is determined by the interaction of modulating species at operator site and RNA polymerase binding. So, basically what it says, if you remember this molecular biology. So, we are discussing about this lac operon. So, here this inducer and repressor activity, where inducer and repressor activities take place. So, we will take one example to understand in a better way. E. coli lac operon promoter operator system. This influence the lac repressor, inducer, DNA interaction on gene expression, and finally, this is the enzyme which is produced is the beta galactosidase. So, we are going to discuss this E. coli lac promoter operator system. As we discussed, it influences the lac repression, inducer, DNA interaction on gene expression, and ultimately that modulates the beta galactosidase activity. So, what we are going to see here, we are going to write enzyme production is proportional to the promoter utilizing efficiency, which can be written as probability that operator site is not bound to the repressor protein. So, this says O naught is total concentration of operator site and O is the available concentration of the operator site. So, now it can be written, this efficiency can be written in terms of probability. So, the fraction O upon O naught can be evaluated by considering the interaction among R, repressor, O and other binding site on DNA designated as D and inducer I, assuming all of them are in the equilibrium. So, we will see how these equations are written. So, this says R is interacting with O and this equilibrium constant is Ka. R is interacting with the D, equilibrium constant is Kb. R is interacting with I, the equilibrium constant is Kc. Similarly, Ri can react with is reacting with O and Ri is reacting with the D. So, these 5 Ka, Kb, Kc, Kd and Ke are the equilibrium constant for the respective equations. Now, let us see species O, it exists in the 3 different form now, that is the O itself, now RO as well as RIO. And if we just see the overall balance on R repressor molecule, then it says R naught, this equals to R plus Ri plus RO, RD, RIO and RID. So, the concentration of non-specific binding site D on the DNA is much greater than the total concentration of R, then we can write D equals D naught. So, we are ignoring here for time being RD and RID. Further, what we are going to do, this once we will solve it, so we are going to neglect the term which will be multiplied with O naught upon R naught, and this gives the final solution of P is directly proportional to K plus D naught into Kb, this is the R plus D, Rd plus Kc, Kc is R plus I. So, it is following a R plus I. So, I is here 1 plus K into D naught divided by just see Kb, Kc, Ke, Ka and Kc, Kd. So, all 5 are there in the denominator and in the numerator, these are the available one. Now, it is very interesting that parameter used in this model can be measured through in vitro experiment. Let us say for the change in the nucleotide sequence of lac operon, it gives to the specific model parameters, and from this we can calculate the effect of change in the repressor level R naught on induced and uninduced transcription rate. So, what is inducer is I and repressor level is R naught. So, these are the parameter value which was deciphered from the experiment. D naught 4 into 10 to the power minus 2 mole, and these are the value of equilibrium constant Ka to Ke. Now, it is very interesting to see here the predicted and experimental beta galactosidase activity. If you see here in the case of wild type, first let us see here. In the case of wild type, when inducer was there, we are considering the activity as 100%. So, wild type in the presence of inducer, we are considering this activity as 100%. This is the predicted value and this is very close to the experimental value. Now, interestingly, if you see this lag knockout cases, when there is a lag knockout, there is no effect of inducer. In the both the cases, we got close to 100%. Now, here we are going to add this repressor molecule. So, this is the, you can see this is the 10x, these two are the 10x and this is further 50x. So, these are the concentration of repressor, and in the both the cases we are comparing in the presence and in the absence of inducer. So, as expected, when there is no inducer, this activity has come almost 0.011, and if you increase further the repressor level, it has become almost 0.002, and further what we are seeing, even in the presence of repressor, when inducer is there, the activity is 62%, but what is happening here, if repressor is further enhanced to 50x, in the presence of inducer, activity is further declined to 23%. And it is very important, if you compare these two columns, the predicted activity is very much comparable with the experimental data. So, what it says here is this, one can fine tune between the repressor and inducer, and why it is happening here in the presence of inducer also, it says the level of the inducer should match with the level of repressor to ensure the 100% activity. So, what we have discussed, this genetically structured model brings molecular details, particularly what we discussed is transcription and translation into kinetics. We discussed one lakh operon example. It gives how we can fine tune between this inducer and repressor, and further it can be extended to multiple genes, pathways and different synthesis routes. Now, next model we are going to discuss is filamentous microbe model. So, if you remember, when we are discussing the growth of filamentous organism, so typically when we see the kinetics of microbial growth, we can write in terms of number of cells, number per unit volume or mass per unit volume. But in the case of filamentous organism, only we can write in terms of mass per unit volume because of their different morphology. And further what we was discussed, the mass is proportional to the T to the power q. But these fungus or molds, they are very important to produce key industrial products like antibiotics, for example penicillin and cephalosporin. Now they occupy different morphology like hyphae, pellets and spores, and depending on the morphology, this nutrient uptake and product synthesis both are affected. So, what it says is, depending on the morphology, the kinetics of substrate utilization as well as product formation varies, and for this classical unstructured model cannot predict these dynamic transitions. Let us say the batch fermentation data for penicillin. So, it has a lag phase, then growth of primary mycelium, then fragmentation of primary mycelium, then growth of secondary mycelium, and then followed by the stationary phase. Typically you see this growth pattern is very different from this bacterial growth kinetics. So, lag phase it varies, typically it says about 90 minutes, then growth of primary micelles it is 10 to 25 hours, then further the third phase is fragmentation of primary mycelium about 10 hours, then growth of secondary mycelium, here this antibiotic production increases, and then followed by then it goes to the stationary phase. So, apart from this penicillin, several other antibiotic fermentation exhibit the similar pattern, but let us say in the case of streptomycin production, the maximum product synthesis rate is found later in the cycle, particularly in this stationary phase, and in the case of this oxytetracycline produced by Streptomyces species, it introduces the importance of morphology for satisfactory performance of fermentation. So, what it says, these 1, 2, 3, 4, 5 steps, they may be there in the antibiotic fermentation, but at the same time this production of antibiotic may vary among different phases depending on the morphology. Now, we are going to discuss one example here, the production of cephalosporin C by Cephalosporium acremonium, now it is called Sacrocladium strictum. So, there are few observations. First, the excess substrate concentration causes the fast fermentation. So, you can see the less product form, when there is a fast fermentation there is a less product formation and maximum substrate is utilized for the biomass production. So, what it says, there should be optimal initial substrate concentration for the maximum product yield. So, we require optimal. So, we are going to balance between biomass growth and the product formation, because if there will be less substrate concentration, then what will happen, there will be less biomass. So, it is again going to affect the product formation. So, we require the optimum biomass, but at the same time if there is a excess substrate concentration, or you can say the fast fermentation, that is not desirable because it leads to the formation of biomass rather than product synthesis. The second observation was the product formation is maximized by minimizing the branching of actively growing hyphae in the inoculum. So, it says it is linked with the morphology of strain. Further, it says a smaller degree of branching, it causes the longer lag time. So, here you have to compromise between this, there is a smaller branching, so lag time is increased, there is a more branching, then it is adversely affecting the product formation. So, now there should be optimum condition of the inoculum, so that this lag time can be minimized, and as well as we should have the optimum product formation. Now, third one is, as this is the aerobic culture, we go for the submerged fermentation. Now, we require optimum mixing. Why? Because there should be sufficient oxygen transfer, and at the same time if you go for the very high rate of mixing, it adversely affects the morphology, because when you apply the force, particularly rigorous mixing, it promotes the branching, and which is believed to decrease the product formation. So, what it says, you just see in all three cases substrate, this morphology in the inoculum and mixing, they are having this dual effect as with respect to the product formation. Now, when we are going to model this, there are certain challenges, because biomass heterogeneity, different morphological states coexist, and further there is a nonlinear interconversion, there may be fragmentation or the aggregation, and these regulatory triggers, the nutrient depletion and secondary metabolite induction, and this mass transfer limitation, as we discussed, oxygen, because this is aerobic fermentation, and here it is coming from the mixing, it impact on the morphology. So, this schematic gives the overall idea how it happens. You can see the morphology hyphae, then swollen, and then this spore. And how it is happening? This is from here to here, it goes due to assimilation of methionine and glucose. There are two substrates, and during the depletion of glucose, this is further converted to the spores. And this swollen fragment is important for the synthesis of cephalosporin, and in this route also you just see induction of endogenous methionine and then catabolic repression by glucose. Then this is the key enzyme, CPC synthesizing enzymes, this lead to the formation of cephalosporin C. So, if you want to mathematical model, so these are the three variables we are going to consider: the hyphal biomass concentration XH, swollen biofragment biomass XS, and arthrospore biomass XA, and in addition these are the interconversion rate. Hyphae to fragment, we are going to consider the beta and XH. Fragment to spore, we are going to consider the gamma and XS. The XH is the concentration of hyphal biomass, XS is the concentration of swollen fragment biomass, and for the spore germination we are going to consider Kp and XA. XA is the concentration of arthrospore biomass. So, first we will do the biomass balance. So, first we will see this biomass balance. So, here we are going to see the mold growth and differentiation. So, as we discussed in the last slide, there are three different morphologies. So, we will be writing three equations: dxh upon dt, dxh upon dt, and dxa upon dt. So, this is typically following this monad equation: mu max g upon kg plus g into xh minus beta. What is beta? Is the fragmentation rate. So, this xh is going for the fragmentation, minus there is a kd is the death rate. Further, if we just see the xh, this is the beta is the term, fragmentation rate into xh, because this is produced from this xh, and there is a minus term which is coming from the sporulation rate. This is going for the spore formation minus the death rate. Similarly, for the XA spore formation, it is originating from the XS minus there is a death rate. So, these are very simple biomass balance kinetics, but now we are writing rather than only X, we are writing based on the different morphology XH, XS and XA. Next is the substrate uptake and intracellular pool. So, there now we are using two different substrates, glucose as well as methionine. And how we are defining this uptake rate? We are defining using this monad equation. UH is U max H m upon m plus Km. Similarly, glucose uptake rate by the swollen fragment is US H. This will be the U max S into m divided by m plus Km. And in the similar manner, we can write the methionine uptake rate by hyphae and methionine uptake rate by the in the fragment. So, Dg glucose is taken by the XH and XS, and this is the glucose uptake rate by the hyphae and glucose uptake rate by the swollen fragment. Similarly, we are going to write the mass balance for the methionine. So, this is the methionine uptake rate by in hyphae and methionine uptake rate in the fragment into the respective concentration. Next, enzyme and product formation. As I told, there is it leads to the synthesis of key enzyme, followed by there is a product formation. So, in the case of enzyme, we are going, it is proportional to the, it is starting with where? If you remember, it is starting with only the swollen biomass is contributing to the enzyme synthesis and product formation. Alpha into XS plus there is a enzyme induction function and enzyme repression function, particularly this catabolic repression function that we will be discussing, because this many times glucose acts as a catabolic repressor here, minus Ke. Ke is the enzyme deactivation rate into E. So, in this way this enzyme is synthesized, and now dP upon dt is linked with this enzyme concentration, enzyme into XS, minus there is a product degradation or dilution rate into P. So, these are very simple straightforward kinetics, but what we are seeing here is first there is a synthesis of enzyme and enzyme concentration is linked with the product formation here. So, enzyme synthesis triggered by the intracellular methionine. So, you just see this induction is done by methionine and catabolic repression is done by G, means glucose, and catabolic repression function decreases E when glucose concentration is high, that is obvious, that is what it is called, catabolic repression function. Now, it is very important to see this, how this model predicts the experimental data. So, you just see here the cell mass. So, all three are given here, swollen biomass, hyphae and this arthrospore, and this is the total biomass. And what we are seeing over here is the points are the experimental data and line are the predicted data. So, your model has predicted the total biomass, hyphae, swollen fragment as well as the arthrospore very well. So, what we are seeing, you just see hyphae is growing, reaching to plateau, and then hyphae is converted to the swollen biomass, and from here this swollen biomass is now converted to the spore. Now, see the next figure here with the time, how this glucose is depleted here. Once the glucose is depleted, then only the synthesis of cephalosporin is taking place, and there is a methionine, and methionine particularly is very important to see this intracellular methionine, its concentration is increasing, it is inducing the synthesis of this particular product, and once it is there, then further it is decreasing. And so, from here to here you just see this intracellular methionine is driving the synthesis of your product cephalosporin. So, it is very important to see during this synthesis there are two substrates, glucose and methionine. One is needed particularly let us say for the biomass growth, time scale if you just see 40 minutes total biomass growth, and the second one is required for the induction of your particular enzyme and the product. So, this gives this idea how we can go for the fed batch system or how we can tune the level of two different substrates. So, what it says, this filamentous microbes demands this morphology based structure kinetics, because this usual unstructured model cannot predict this behavior, and this model interestingly captures the interconversion among all three morphologies, hyphae, fragments and spores, and it guides this intercellular metabolites, guides this enzyme synthesis, and this, as I discussed, once we know how the substrate are affecting the rate of product formation, one can design this batch and fed batch strategy in a better way. So, with this I will stop here. So, today we discuss first this genetically structured model, where we first see the transcription kinetics followed by the translation kinetics, and in the case of filamentous organisms we discussed the biomass kinetics based on three different morphologies, and particularly then the swollen morphology leading to the synthesis of your enzyme, and enzyme is leading to the synthesis of your product. So, with this I will stop here. Thank you so much.